Kernel Adventures Part 1 was a very fun binary exploitation challenge from HackTheBox, which involved exploiting a double fetch race condition in a kernel module. Let's have a look at it now. Out of the box, we are given 4 files: a kernel boot image, some additional notes by the author, the root file system, and a shell script to run this VM in QEMU. Let's start by extracting the file system and having a look at the init file. You can see that after some environment setup, it does two important things. Firstly, it inserts the mysu kernel module. Next, it loads up a shell for us by being logged in as UID 1000. This machine actually has 3 users. One of them is root and the other two are unprivileged. When we spawn the machine, we will be logged in as user, and our goal will be to exploit this vulnerable kernel module to do a vertical privilege escalation and gain root access. So let's begin reverse engineering this kernel module and find some vulnerabilities. If we briefly take a look at the init module function, we see that it registers a character device which we can interact with by using the read and write syscalls. When we read from the device, the module allows us to read up to 32 bytes from the user struct. What is the user struct, you may ask? Well, the user struct has two user profiles inside it, and each user profile has an ID and hash field, both of which are 32-bit unsigned integers. So when we read data from this device, we will be leaking these two users' profiles. Now let's see what happens when we try to write to it. Well, first of all, the kernel expects us to provide a pointer to the user data struct. Then it matches the provided ID with 1000 and 1001. If it is either of these two, then we go on to compute the hash of the given password. If the hash matches with the one stored in the user profile, then we finally reach this code block. Here we call prepare creds. That will give us a pointer to a newly allocated cred struct. After that, it will set the real, saved and effective UID and GID to whatever ID we provided when calling this function. So overall, we give this function an ID and password. If the password hash matches, we switch to that user, much like how the su command behaves in the terminal. But if you think about it, we can only switch to user or admin, and that's practically useless because both of them are unprivileged users. Instead, what we would like to do is switch to root with ID 0. But if we directly set ID to 0, we would never reach this code block in the first place because the very first if condition will block us out. So what do we want? Well, we want the ID to be 1000 when this check happens, but we also want it to change to 0 just before we reach this code block. At first, this seems impossible, but if you think about it, it's pretty obvious. This is a classic case of a talk-to race condition, or more specifically, a double fetch vulnerability. Because at the time of check, we fetch the profile to get the ID, and at the time of use, we fetch it again. The thing is, profile is a pointer to a user space memory location, and that memory is completely managed by the user space process. This means that there could be multiple threads trying to concurrently mutate the ID field, and the kernel could easily be in a situation where, let's say, thread 1 writes 1000 into ID, then the kernel uses it and goes on to compare the hash. While that is going on, thread 2 comes into picture and decides to write 0 into ID. The kernel finishes comparing the hash and moves on to this code block where it fetches the ID again. This time, since it has been modified to 0, so all the ID fields of the cred struct will also be set to 0, and upon committing it, we will be root. I think it's a solid plan, except we ignored an important part, which is the hash function itself. And I have no idea how to explain this because it just works the way it does. For obvious reasons, it cannot be reversed. So, to come up with a solution, you would typically need to use something like Anger or Z3. But there are two problems. Firstly, I don't know either of these. And secondly, the hashes in this version of the kernel module have been cleared out. So, we don't know the real hash until we connect to the remote machine and dump it out ourselves. Considering these two factors, I think it's a lot of work, so I choose to just brute force it at runtime. Because technically, we are talking about 32-bit unsigned integers. It's just 4 billion of them. And with level 3 optimization on modern compilers, I don't think it will take a very long time. So let's build the exploit. First, we open the character device. Then we use read to leak the hash. Then we use plain old brute force to crack it with level 3 optimization on this function to speed it up a little bit. Then we begin the race, where we will spawn two threads. One will constantly reset the ID to 1000 while the other will set it to 0. Meanwhile, the main thread is continuously going to write the profile until our UID becomes 0, because when it does, we have won the race. because when our UID is 0, we have become root. After that, we can simply spawn a shell and profit. And yeah, that's the entire exploit. Let's compile it and rebuild the root file system and start our VM to test the exploit. Well, that worked quite well. So let's quickly make a solve script to transfer our exploit to the remote system and see the result. And with that, we finally compromise the system and get root. If you are looking for the final solve script, I have already uploaded it to my blog, which I will have it linked in the description of this video. So yeah, that's it. Very fun challenge and thanks for watching.